Hello everyone, welcome to the 5th week of the course Process Equipment Design, and here we are with lecture 21. Okay, and this is the first lecture of 5th week, and here we are going to discuss design of shell and tube heat exchanger using Bell's method. In 4th week, we have discussed design of shell and tube heat exchanger using Bell's method and different steps involved in that. And further, we have seen one example in 5th lecture of last week. Okay. And here we are illustrating the design of exchanger using Bell's method with few more example. So, let us start with example 2. Okay. So, in this example, you have to calculate heat transfer coefficient of shell side of a shell and tube heat exchanger using Bell's method for following specifications. Here we have to consider toluene, which is basically an organic liquid with 40,000 kg per hour flow rate, and it is cooled from 60 degree to 15 degree Celsius in a heat exchanger. 80,000 kg per hour of water is used, which is available at 5 degree Celsius, and this we can consider as cooling media. Densities of toluene and water are given like this. Okay. And here we are given shell dia, and here we are given shell dia as 531.2 mm, and this is not OD, this is basically shell dia. Okay. Pitch is given as 0.02375 meter and outer diameter of tube is given as 19 mm. So, you see here we are given some specification about the problem, and if you see this problem, this is the same problem which we have discussed in 4th week, and if you see the first lecture of that week, where we have illustrated the design of shell and tube heat exchanger using Kern's method. Okay. So, the same example I am considering over here, but here we should apply Bell's method. So, as far as heat transfer coefficient in tube side is concerned, that you have already covered in the first lecture of week 4. So, I am not going into detail of that. I am starting from Bell's method when it should be considered to shell side heat transfer coefficient, right. So, let us start this. So, here as you know that when we apply Bell's method, the first parameter we have to obtain is HOC, which is the heat transfer coefficient on ideal tube bank, and then we will add other correction factors to find out actual shell side heat transfer coefficient. Okay. So, if you see when we calculate GS, we have considered 40,000 kg per hour as the mass flow rate, and which is of toluene. Okay. Because when I compare toluene and water, you can understand that water is more corrosive, water has more fouling tendency. So, it should be allocated to tube side. So, toluene should be considered in shell side. Fine. So, considering that, we can find out GS value, which comes out as 1182.03. right. And further we have to find out baffle spacing. So, here I am considering ds by 4. Okay. And I can also find out cross flow area, that is AS, which is basically based on baffle spacing as well as shell dia. Okay. So, AS value you can obtain as we have discussed in previous examples in Bell's method and Kern's method. Considering these, we can obtain shell side velocity as 0.911, and that should be US, right. So, if I compare this velocity, it is basically falling within the range, because it should be within 0.3 to 1 meter per second. So, whatever US we have obtained, that we can accept, fine, right. And as far as viscosity of toluene is concerned, because that will be used to find out Reynolds number. Okay. And viscosity of toluene, water, all these we have already seen in the first lecture of 4th week. So, we can simply use these values instead of collecting the properties again. Okay. So, once you have the viscosity of toluene, you can find out Reynolds number, which is coming out as 3.119 into 10 to the power 4, and corresponding to this we can find out JH factor. Okay. So, here it should be JH. So, we can find out JH factor depending upon the Reynolds number, and further we can find out Prandtl number. So, it comes as 10.001, and we can ignore viscosity correction factor. So, that I have equated to 1, and further you can find out HOC value using this expression, and value you can obtain as 1499.55 watt per meter square degree Celsius, because I am having Reynolds number more than 2000. Okay. And after that, once I am having HOC value, after that we have to find out different correction factor like FN, FW, FB and FL. Okay. So, to start this, we should first focus on FN correction factor. So, let us start that. So, as far as this FN correction factor is concerned, this will depend on NCV value, because Reynolds number in shell side is more than 2000, right. So, we have to find out FN value from the graph, which will be based on NCV value. So, first of all, let us focus on NCV value, and this is the expression for NCV, and here it is equal to ds minus 2 Hc by Pt dash. So, if you see here we have considered slightly different expression. Usually it is dB minus 2 Hb by Pt dash, right, but here I am considering ds minus 2 Hc by Pt dash. Okay. Now, if you consider the cross sectional view of shell, here I am having the baffle. Okay. This is the complete cross section of shell, and this is basically Hc value. Okay. So, ds is this, and Hc is basically the cut, the height of cut section of baffle, right. So, this is ds. If I am considering baffle cut of another baffle, this is further Hc. Okay. So, NCV is what? NCV is basically number of tube rows between two baffle tips, right. So, that I can find as ds minus 2 Hc also by Pt dash. So, both formula will be applicable, either you use dB minus 2 Hb by Pt dash, or you can use ds minus 2 Hc by Pt dash. In both way we can find same HCV value, right. So, considering these parameters, because I already know ds, I also have calculated Hc value, which is 132.8. So, considering all these value, we can find out NCV as 12.85, which should be round up, and the value I am considering final, and the final value of NCV I am considering as 13. So, you can find out Fn from the graph where, so you can find out Fn from the graph of Fn and NCV. So, Fn value you can find as 1.01, right. So, now we have to find out window correction factor, and for that I should know Rw, and for that I should know Ra dash. I hope you remember all graphs and steps. Now, if I need to know Ra dash, I have to find out bundle cut. Okay, and bundle cut will be nothing but Hb by dB. So, here you have to find out Hb value again. So, Hb should be equal to dB by 2 minus ds bracket 0.5 minus 0.25, because I am considering 25% baffle cut. So, you can find out Hb value, and then bundle cut you can find as 0.244, right. So, value of bundle cut you can find out depending upon the number of tubes, and this is already available in first lecture of week 4. So, for all these calculation you can please go through that lecture, so that you can understand. But I hope if number of tubes are given to you, you can find out baffle, you can find out bundle diameter, right. So, here I am having baffle cut as 0.244, and Based on that, I can find out RA dash, which comes out as 0.178, and so we can find out RW just twice of RA dash, right. And after that we can consider graph of FW. Okay, if you remember, we have seen the graph of FW as well as RW, right. So you can find out FW value as 1.04. Okay. And further we can see bypass correction factor as well as leakage correction factor. Okay. Now if you consider bypass correction factor, we have to find out whether sealing strips are required or not. Okay. And that checking of sealing strip, whether it is required or not, that method is already explained in the last lecture, that is the 5th lecture of 4th week, right. So you can please go through that. If you consider the FB expression, there I am having alpha AB by AS and we have NS by NCV. So maximum number of sealing strips you can use as 6, because NCV you can have is 13. So AB and AS, the way we have obtained that in the 5th lecture of week 4, in the same line you can find here also. So considering all these value, if I am putting NS equal to 0 in FB, okay, if I am putting NS equal to 0 in FB, depending upon the obtained value of FB, you can decide whether sealing strip is required or not. Okay. So let us see that calculation. AB you can find out by this, where this is LB and that should be equal to DS and minus DB. Okay. So AB you can find out as this, and AS you have already obtained like this, and NCV you have already obtained as 13. And when I am putting NS equal to 0 in FB expression, actually here I am not showing FB expression, because that expression is known to you. Okay. So I have directly put the value in the expression, and here I am showing the values directly. So if you are using NS equal to 0 in FB, alpha here is 1.35, as you have Reynolds number more than 100. So you can find out FB value as 0.853, and you can see that this value is already more than 0.6. It means sealing strips are not required. Okay. In this case, sealing strips are not required. Okay. So here I am fixing, so here I am considering FB value as 0.853 only, but here you should find revised FB value from the graph, and that graph is between FB and here I am having AB by AS. Okay. So value you can obtain from this graph depending upon the Reynolds number, and that value you should consider as final FB value. Okay. So please consider that here I am not considering that value, and which is the mistake, and I apologize for that, because for further calculation I have used this value directly, but that is not the correct method. Okay. The correct method I have already explained to you. Okay. So please consider my apology for this. So next we will find out leakage correction factor. Okay. Next we will find out leakage correction factor, and for that you should find out value of ATB and ASB, right. And in ATB expression you should use CT, which is equal to 0.8 mm, which is the fixed value in all cases, and in ASB you have to find out CS value, right. So you consider CT as 0.8 mm. Okay. We have total number of tubes as 368, and NW we can find out as 65, and ATB you can consider as 7234.46 mm square. Shell diameter is already given to you. So corresponding to shell diameter you can find out CS value from the table, where from the table where shell dia and baffle dia are given as per the shell dia range. Okay. So, depending upon all these value you can find out ATB and ASB, but for that you also require theta B value. Okay. So, that theta B value you can obtain as 2.08 and which is corresponding to 25% baffle cut, right. So, you can find out ASB value as 1786.18 mm square, and then you can find out beta L value from the graph and so the FL value. So, FL value comes over here as 0.321. Okay. So, now you have all 4 correction factors and HOC value. So, you can find out shell side heat transfer coefficient by simply multiplication of all these, right. So, simply you have multiplied all values of correction factors with HOC, and here you see I have considered FB as 0.853, but you should consider FB value from the graph and then you should use over here. Okay. And then you should use that value here. Okay. So, final heat transfer coefficient in shell side you can obtain as 431.29 watt per meter square degree Celsius. Okay. So, this is the solution of example 2. Now, I am considering another example where we are using Bell's method to find out pressure drop. Okay. So, here I am having example 3 as a fluid with 35,000 kg per hour is flowing in shell side of 1-2 shell and tube heat exchanger having following specifications, where OD of the tube is 25 mm, ID of the tube is 20 mm, shell diameter 1000 mm, number of tubes are 600, baffle cut 25% and baffle spacing ds by 3. Right. A square pitch arrangement are given and number of sealing strips are 4. So, here we have already fixed the number of sealing strips. So, here we have already fixed the number of sealing strips. Density of the fluid is 550 kg per meter cube. Okay, and viscosity of the fluid is 0.09 millinewton second per meter square, and what we have to compute is cross sectional flow zone pressure drop using Bell's method, right. So, for this problem we have to find out cross flow zone pressure drop, and for that you need bypass correction factor as well as leakage correction factor. Okay. So, let us start the calculation. So, when you consider the pressure drop in cross flow zone, you have to find out delta Pi, and delta Pi is basically the pressure drop in ideal tube bank, right. Now, if you recall the expression of delta Pi, it consists NCV, US and other parameters. So, we have to find out US, that is the shell side velocity at bundle equator, and that will depend on AS value, right. So, let us start the solution of this problem. If you see here I am having OD of the tube as 25 mm, shell dia 1000 mm is given, number of tubes are given as 600, baffle cut 25% and baffle spacing which is equal to ds by 3, right. So, 1000 ds is given. So, 333.33 is the baffle spacing. Mass flow rate is given to us, which is 35,000. Square pitch, because 25 mm is the OD. So, you can find out square pitch. So, you can find out the pitch, which is 1.25 into OD. Density of the fluid is 550, viscosity 0.09, right. And here we have all expression to calculate AS, and AS you can find out using this expression, and value of AS you can consider as 0.0667 meter square, and in the similar line we can find out shell side velocity at bundle equator, which comes out as 0.26515 meter per second, right. So, considering shell side velocity as well as the property you can find out Reynolds number of shell side, and it comes out as 40509.25, which is in the turbulent zone, and you can consider JF factor to find out delta Pi. Okay. And the JF factor you can obtain from the same graph which we have used in 5th lecture of 4th week. Okay. So, that we have already illustrated. So, I am considering value of JF directly, which comes out as 0.05, right. So, if you see, we have already obtained US value. Now, we have to find out NCV, because then only I can calculate delta Pi. So, to find out NCV, we have to find out bundle diameter. So, OD of the tube is given and number of tubes are also given, which is equal to 600. So, you can consider 1 to pass, and for that K1 and N1 value you can obtain corresponding to square pitch, and bundle diameter corresponding to 600 tubes you can find using this expression. Okay. So, there is nothing new, you can, so there is nothing new, you have already used this expression many times before. PT dash you can also consider, which is PT dash you can also consider as equal to PT, because I am having a square pitch now. So, HC value you can consider as 250, ds minus 2 HC you can find as 500, and NCV value based on these, and NCV value based on all these you can find as 16, which is basically the total number. So, you do not have to do anything, you should consider NCV 16 directly. Okay. So, once you have NCV value, you can find out pressure drop in ideal tube bank using this expression and neglecting viscosity correction factor. So, based on all these value, you can find out pressure drop in shell side, you can find out pressure drop in ideal tube bank, and which is coming out as 123.737 Pascal, right. And now, we will further calculate bypass correction factor as well as leakage correction factor. So, let us start with bypass correction factor. Now, in this problem, number of sealing strips are already fixed, which is equal to 4, right. And you have this expression of FB where alpha value is equal to 4 also, because it is in the turbulent zone. So, AB you can obtain from this, because you already know DS, DB and LB. So, AB value you can obtain. Now, considering NS equal to 4 and NCV as 16, you can find out NS by NCV as 0.25, and then considering all these values in this expression, you can find out FB dash as you can find out FB dash as 0.7127. Okay. So, in that way you can find out bypass correction factor for pressure drop calculation. Therefore, we are considering FB prime. Okay. In the similar line, we should also carry out FL prime, that is leakage correction factor for pressure drop. Okay. So, to consider that, we can use this expression, that is FL prime should be equal to 1 minus beta L ATB plus 2 ASB by AL, right. And ATB expression is given over here and ASB expression is given over here, which you have already used previously. So, I am not going into detail of this, just I am telling that how we can obtain different parameters. So, CT value is already fixed as 0.8, NT 600 is already given. Now, you have to find out NW, and for that you have to find out RA dash, okay, because NW is equal to NT into RA dash, and for that RA dash you have to find out bundle cut, okay, and that should be equal to HB by DB. So, first of all you have to find out HB using this expression, and the value of HB comes as 208.92. Once you have this value, HB by DB you can consider, which is coming as 0.2276 as bundle cut, and based on that you can find out RA dash value as 0.17. Okay. Now, once you have RA dash value and total number of tubes, you can find out NW as 102. Okay. So, based on that you can find out ATB value, which is, so based on that you can find out ATB value, which is coming out as 0.01565 meter square. Okay. And further I have to find out ASB, and for that theta B value should be seen from the graph. Along with this CS is also required. Okay. So, what should be the CS value? For that we should consider this table where the diameter is 1000, so which will fall in this range. Okay. And if I consider CS value, this should be the CS value, right. So, in this case CS value should be 4.8. Okay. And considering baffle cut, you can find out value of theta b from the graph. So, baffle cut is 25% and theta b we can obtain from the graph as 2.1, which we have also seen in last lecture of 4th week. So, you can go through that lecture, and considering all these value I can find out ASB as 0.01004, and then we can consider AL, which should be equal to ATB plus ASB. Okay. So, addition of all these will give the value of AL, and then after that we can find out ratio of AL by AS, and based on that I can see the value of beta L from the graph, right. So, that value of beta L comes as 0.48, and based on that I can find out FL dash value using this graph, and which is using this equation, which is coming as 0.0, which is coming at 0.3324, right. And accordingly I can find out pressure drop in cross flow zone, and that should be equal to delta Pi into Fb dash into Fl dash. So, in this way you can find out pressure drop in cross flow zone, and detailed calculations of that I have already explained in the 5th lecture of week 4. However, here some of the steps I have skipped because I am just because I assume that the method is clear to you, and you can simply apply that method. Okay. And that is the Bell's method. And here I am having some of the references, and now as far as this lecture is concerned, let me summarize this lecture. In this lecture we have discussed two different problems. In the first problem we have calculated shell side heat transfer coefficient using Bell's method, and in second example we have discussed pressure drop of cross flow zone using Bell's method. So, I hope the method as well as examples are clear to you, and you can apply Bell's method to design shell and tube heat exchanger, and that is all for now. Thank you.